everyone. I'm Jyoti Sharma. Once again in front of you, taking one of the complex topic that is DC motor characteristics. This is the topic which is covered under the syllabus of first year under AKTU, having a subject code of BW101. Now, to have understand the DC motor characteristics, first we should know what is the torque equation of a DC motor. In fact, in our previous lectures, we have covered the DC generator, the EMF equation for a DC generator, how this induced EMF is related with the speed. What is back EMF in case of motor? We have studied this. Now coming to the torque equation of a DC motor. So if at all we just see the torque equation, what do we exactly mean by a torque? A torque is nothing but it is the turning or twisting force acted upon on a circumferential basis. That means about an axis. That is what we call it as a torque, right? So if at all we just consider to have our relationship. So just if at all I consider that a wheel is there, right, of radius, say r meters, right? The radius is r meters. It is acted upon by a circumferential force F newtons. It is acted upon by a force of F newtons. So it is rotating in, say, clockwise direction. This is its direction. Then now, if that is so, if this is having a speed of n rpm, if this wheel is rotating at a speed of n rpm, right, then its angular speed omega, that is given by 2 pi n by 60 radians per second. That is okay. With that, if at all I say, what is the work done in one revolution? So the work done in one revolution, that is equals to, this is work done. The work done in one revolution is equals to the force applied multiplied by the distance traveled in one revolution. So the distance traveled in one revolution, that will be 2 pi r. This is the work done, right? If that is so, what is the power actually developed? The power developed while doing this work, that is given by the work done upon time. So the work done in one revolution by the time taken for one revolution. The work done in one revolution by time taken for one revolution. So the work done, we have just got it off as F into 2 pi r. The time taken for one revolution. The time taken for one revolution. The speed of the wheel, that is, say, n rpm. That means n revolutions per minute. That means n revolutions in 60 seconds. If that is so, how much time would be taken for one revolution? So it is going to be 60 by n, right? So the time taken for one revolution is 60 by n. Right? Now rearranging this term, I may have it as F into R and then 2 pi n by 60. So once again from here, this F into R is nothing but the torque, force multiplied by the radius, right? That will give me the torque produced. 2 pi n by 60, we have already defined it. This is nothing but the angular speed omega of the wheel, right? So what is the relation we are getting? That the power developed is equals to the tau, that is torque multiplied by the angular speed of the wheel. Let's putting this as our base equation and just apply the same base equation for a DC motor, right? The torque in DC motor, the torque is generated or developed in the armature, right? So I used to call it as armature torque given by tau A, right? And the power developed, the gross mechanical power developed is also in armature. So I'm calling it as PA. And this is the angular speed of the armature, considering that the armature is rotating at a speed of n rpm, right? If that is so, once again, I can be giving this PA is equals to armature torque into omega, which is nothing but 2 pi n by 60. Once again, this power developed in the armature. How much is the power, gross power developed in the armature? So if at all I give the electrical equivalent of the gross mechanical power developed in the armature, that will be the EMF in the armature, that is what we call it as back EMF, EB, and the current which is there in the armature, that is being called as IA. So the gross electrical equivalent of the gross mechanical power developed, that will be given by EB into IA, and that must be equals to tau A into 2 pi n by 60. Once again, this back EMF, we know its value is nothing but it is equals to the generated EMF, what we have earlier derived in our earlier lectures. This is given by phi p n z by 60A into IA, which is equals to tau A into 2 pi n by 60. Where once again, what is this phi? The phi is flux per pole, the flux generated by individual pole. P is the number of poles of the field. N is the speed of the armature at which it is rotating. Z is the total number of conductors on the armature. A is the number of parallel paths and depends upon the kind of armature winding. If it is a lap winding, then this A is going to be, if it is a lap winding, this A is going to be equals to the number of pole for lap. This is for lap. And if it is a wave winding, then this A is always going to remain 2. We have seen this in case of the two types of armature winding, that why the parallel paths are equals to number of poles in case of lap and in case of wave, why it is 2. So now, once again, going for the expression and deriving the expression for tau A from here. If I derive the expression tau A from here, it will be 1 upon 2 pi phi IA PZ by A. Right? This 1 upon 2 pi, if at all I say, this is nothing but 0.159 phi IA PZ by A. This is nothing but the net torque produced in the armature. The important thing to notice, this is an expression, the important thing to be noticed over here is, as this is constant, as well as PZ by A, this is also constant. So I may be saying that the torque is actually proportional to phi IA. This is a very important conclusion, because based on this conclusion, we'll be going with the characteristics of DC motor. Thereby, those characteristics will decide which kind of motor would be suitable for which kind of job, which kind of applications. So we got the torque equation. Now coming to various different kinds of motors. In fact, we have seen this, giving the brief glance of that, and with that we'll be continuing with their individual characteristics. So first of all, if at all I take a DC shunt motor, right? If it is a DC shunt motor. A DC shunt motor, how do we represent it? The symbolic representation for a DC motor and its circuit. Symbolic representation, it's a DC shunt motor. That means the field would be connected in shunt with the armature. This is a motor, and we know that if it is a motor, obviously it will be connected to certain mechanical load. Its armature is connected to, its shaft is being connected to a mechanical load. This is field having a resistance of say RSH. The current being flowing is say ISH. It's a motor, so the supply has to be fed. Say that supply is what we are calling it as V. So we are having the current. This is the line current taken by the motor from the supply. And from the same supply, the armature would be fed, having an armature resistance of RA, having a back EMF of EB. If that is so now, I can be having now the relations. I'm having three currents. So the relations are IL is equals to IA plus ISH. This is the incoming current, the total current taken by the motor. The current in the armature is IA and ISH. Once again, ISH. How can I give the expression for ISH individually? ISH can be given as, what is the voltage across this RSH? That is nothing but V. So ISH is equals to V upon RSH. Right? Now, what is the relationship between this back EMF and this voltage? Right? If at all I just see now the polarities. This is positive, negative. The current is getting in. And then once again, the drop, positive, negative. Here once again, it is positive. Here it is negative. So if at all, once again, I apply my KVL in this loop, the equation what we'll be getting is V is equals to EB plus IARA plus the reactance drop is also there, but presently we are considering them as to be negligible. Considering the brush drop or the V brush, we used to have small amount of drop which are occurring in the brushes as well, which is generally 1 or 2 volt per brush. So I'm taking that into account, but presently we are not taking into account the cross magnetization effect or the reactance drop, what we'll be getting, right? So we are going for the back EMF, the armature resistance drop, which is IARA, and the brush drop, which we are representing with as V brush. Now, if that is so, these are the current and voltage relations. Let's see the characteristics for a DC shunt motor, right? So the characteristics we are going to study are all the output characteristics, means the output, at the output we used to have the speed, the torque, the armature current, which varies according to the load. If that is so, I may be having now 3 graphs. One is the curve which is representing torque, the armature torque versus armature current, right? Another one is the graph which is representing speed versus armature current. And another is the graph which is representing speed versus torque, armature torque. If that is so, now torque versus armature current. Now what is the relationship between torque and the armature current? We have just studied it. We have just derived it. For any kind of DC motor, the relationship between torque and armature current, we just derived that the armature torque is proportional to phi Ia, right? But a DC shunt motor is a constant flux motor. Constant flux, why? Because in case of DC shunt, if at all I see, this is the field winding where the flux would be produced. If at all I say flux, this flux must be proportional to ISH. Right? But how do we give ISH? ISH is given by V upon RSH, where V is also constant, RSH is also constant. Right? So it is a constant flux motor. So in case of DC shunt motor, it is also being called as a constant flux motor. So the flux is constant, right? If that is so, in this expression, torque is proportional to phi Ia. Phi is constant. If phi is constant, obviously, torque becomes directly proportional to Ia. So what will be the nature of the graph? It will be a straight line. Right? In the same, if at all, this is the armature torque. I may even be plotting the shaft torque. What is shaft torque? The torque which is actually available at the shaft, which is a slighter, lesser value compared to the armature torque, because while transferring the torque from the armature to the shaft, we used to have a small amount of torque which gets lost because of the friction and windage losses. It has to cover up those losses, right? To cover up those losses, the torque is being lost. So the shaft torque is comparatively lesser than the armature torque produced, but will be having the same nature. So in fact, I may just show it like this. This is nothing but the shaft torque, and this is nothing but our armature torque. Right? Now, coming to the next characteristics, that is speed versus armature current. Now, what is the relationship between speed and armature current? We have just seen EB, how it is related? I know that the speed is inversely proportional to back EMF by flux. Back EMF is given by phi p nz by 60A. Rest of the things are constant. So the speed is proportional to back EMF and flux. They will vary according to the load, right? But once again, flux is constant in DC shunt motor. So speed is just proportional to EB, right? And EB is given by, how do we give EB in terms here? EB is given by V minus IARA minus V brush, right? So substituting that V minus IARA, I'm also neglecting V brush, which is hardly 1 or 2 volts per brush. So it is V minus IARA, right? So if at all I see this, if at all the armature current is increased, right? Obviously, if the armature current is increased, it can be seen this IARA drop will also increase. That means the armature resistance drop will increase, right? So obviously, this V minus IARA drop, that should decrease. But by how much? Will it change drastically? Right? No, not because this armature resistance is very small value. The resistance of the armature, that is a very small value. That's why this drop will not be very much significant. It is not going to make a very significant decrease in this terminal voltage, in this voltage, right? Or in the back EMF. Because that is going to remain V minus IARA. This drop is not there. So I may just say that EB is almost equals to V, which is a constant. So the speed is going to get decreased, but it will not be much significant, right? So if at all this is the base speed, if at all I say this is the base speed of the motor, the no load speed of the motor, in that case, now when the armature current is increased, right, up to the full loaded condition, then in this case, the characteristics would be, I'll be getting a drooping characteristics, but it will not be very much significant. So the speed will decrease, but it will not decrease significantly. It is a fairly constant speed. So here I'll be using DC shunt motor for the applications where we require fairly constant speed with not much of the variation. And also, the torque produced is neither very high and neither very low. It is a moderate starting torque which it will be producing in case of DC shunt. Now, coming to the last, that is speed versus torque. Now, this characteristics, it is very easy to understand, right? The same characteristics can be drawn from the earlier two. We have just seen the characteristics for speed versus armature current, right? And we also know that this armature current is just directly proportional to the torque from the earlier one. We have just derived that the torque is directly proportional to armature current. Armature current is directly proportional to torque. It means I may be having the same kind of nature of the graph for speed versus torque. So if this is the base speed, so the nature of this characteristics would be slightly drooping. This is for DC shunt motor. Now coming to DC series motor. Let's say it's a DC series motor. Once again, how can we represent a DC series motor? In this case, the field windings would be connected in series with the armature. The supply would be given as that of V. This is a motor. Obviously, a mechanical load is being connected with its shaft, but presently I'm not showing it. It is understood it's there. So, I'm having the back EMF. Then, this is the line current. This is the line current. Then the field current, I am naming it as ISC, the series field current. The resistance is RSC, the armature current IA, and the armature resistance RA. If that is so, once again, I am having three currents. The relationship between the three currents is IL is equals to ISC is equals to IA. All the three currents are same. It's a constant current generator in case of generator, and it's a constant current in a motor. If that is so now, so IL is equals to ISC is equals to IA. Voltage equations, there will be a change in the voltage equation now, right? Once again, the polarities. positive, negative, positive, negative, positive, negative. So once again, E is equals to EB plus drops. Which drops? The armature resistance drop, the brush drop, and also one more drop would be added, which is nothing but this series field winding drop. This would be added this time. ISC, RSC plus V brush or the brush drop. Right? Now, going with the characteristics. Once again, seeing the DC motor characteristics. So the very first characteristics what we were seeing in the earlier case also, that is armature torque versus armature current. What would be it like? Now, once again, the relation is the same. Torque is proportional to phi Ia for any motor. But we also know that for a DC series motor, the flux is not constant. It is for a DC shunt motor. Then, if it is not constant, then it is varying according to the flux is proportional to the current which is flowing through the field winding. And what is the current flowing through the field winding? Ia. So, the flux that is proportional to Ia, so that the torque becomes proportional to Ia square. So, here the armature torque is proportional to the square of the armature current. So, the nature would be this. In fact, the nature is this up to saturation, right? Once the saturation occurs, the flux becomes constant, and after that we'll be getting a straight curve. But that region is not much of use because the same characteristic we used to get for shunt as well, right? Directly proportional. In this region, the torque generated is, the starting torque is very high for a DC series motor. So its application belongs to those areas where we require a higher starting torque. All the lifting, all kinds of lifting jobs, likewise elevators or cranes or hoist or trolleys or electric locomotives, traction, there we used to go for DC series. Now, coming to the second characteristics, that was speed versus armature current. Now, if this is the base speed, once again, the relation is the same. The relation is speed is proportional to back EMF by flux, but this time flux is not constant. Likewise in DC. In this case, flux is now proportional to Ia. What about EB? Just getting the equation from this. EB is equals to V minus IRA minus ISC minus V brush. So once again, EB can be written as V minus IARA minus ISC RSE. Right? But once again, if I increase the armature current, which is equals to ISC, the resistance, armature resistance as well as series field winding resistance, these values are very small. So these drops are not going to be very much significant. If these drops are not very much significant, it means that EB is remaining almost equals to V, which is a constant. Or I must say that now the speed becomes proportional to V upon Ia, but V is constant. So the relation what I am getting is N is inversely proportional to armature current. So the graph we'll be getting is of this sort, right? From here, we could say that a DC series motor should never be started on no load condition, right? It can be very much easily seen that towards the no load side, right, when the armature current is very small, at that side, the speed of the motor is dangerously high, infinitely high, which may permanently damage the motor. That's why a DC series motor is never started on no load condition. Moving on to the third characteristics, which is once again speed versus torque. Now, speed versus torque characteristics. How to go with this? Once again, this characteristics can be derived from the earlier two characteristics. In the earlier characteristics which we have just seen, that speed is inversely proportional. Here we have seen that speed is inversely proportional to armature current. And how armature current and torque are related? Torque is proportional to Ia square, or Ia is proportional to under root torque, right? So I may even say that speed is inversely proportional to under root tau A. So the nature of the curve remains same. It's inversely proportional. Right? So this is for the DC series motor. Now coming to the rest of the two motors. The two motors based upon applications we are going, right? In fact, it is a DC shunt motor what we have discussed, series motor. Now a compound motor where we used to have series field winding as well as shunt field windings, right? But with that, depending upon the construction, we may be having long shunt, short shunt, and depending upon the working principle, we may be having it as cumulative and differential. As we are heading towards the characteristics and we are heading towards the applications, we'll be going with the cumulative and differential, right? In case of now, I'm just going with the characteristics. In case of differential, we'll be having, this time we'll be plotting all the three. All the four types in the same, right? So the very first characteristics is for the torque versus armature current. The another one was speed versus armature current. And the third one was speed versus torque. Fine. So let's draw it for a shunt. So we have just seen that for a DC shunt motor, the torque is going to remain directly proportional, right? If it is the base speed, the speed is going to get decreased for a DC shunt. This is for a shunt characteristics. This is also for a shunt, having this as our base speed. Similarly, say this is our base speed and this would be the shunt characteristics. Similarly, we can be having series characteristics, right? But the DC series motor, it will be having its torque greater than the shunt because the shunt used to produce a moderate torque, but a DC series motor used to give us a higher starting torque up to saturation, and after that it may be a straight curve, right? This is series. Similarly, we have just seen in case of speed versus armature current, it is going to be inversely proportional. The speed is going to be inversely proportional. This is for series. The same is the curve for speed versus torque. Now, plotting the characteristics for cumulative. Now, if it is a cumulative motor, what does the characteristic says? That for a cumulative, what is a cumulative motor? Where it is a cumulative, it is the addition. That means the flux created or the field created by the shunt field windings and the series field windings both supports each other. Both of them are in the same direction. If that is so, likewise, let's have the discussion. Say I'm having a single pole, right? And on this pole core, I'm having both the windings being wound. One is the series field winding, another one is the shunt field winding. So the series field and the shunt field. Now if the flux produced by the series field winding, obviously that will depend upon the current. So if the field created by or the flux created by the series field winding is say in upward direction, and the field created by the shunt field winding is also in the upward direction, then both the total field would be the addition of the two, right? So the total field would be phi SC plus phi SH. So it will be a stronger field. Both of the fields supports each other. So the net field would be the addition, the accumulation of the two. That's why this sort of motor where the shunt field flux and the series field flux supports each other, there we used to call it as cumulative motor. Whereas in case of differential, what is going to happen? One of the direction may be reversed. So if at all the flux created by the shunt field winding, if at all I say that is in opposite direction, then what will be the total flux? The total flux would be the difference of the two. Thereby it is named as differential motor, right? Differential compound motor. So if that is so, let's go with the characteristics. So if at all I want to plot the characteristics for a DC cumulative compound motor, so in that case it is having series as well as shunt windings, both. So it will have the advantages from both, right? What is the advantages of series? That it produces a higher starting torque. So the starting torque is nice enough, right? And also the no load condition, which was not permissible in case of series, right? That condition is also possible. So every time we can be seeing that the cumulative would be plotted in between the series and shunt. This is for cumulative. Right? It is giving a nicer starting torque, greater than shunt but lesser than series. Similarly, in this case, it can be started at no load. Right? So I'm having a no load speed. It will be drooping, it will be decreasing, but not as that of series. And the no load condition is also permissible. The same kind of graph will be getting for the torque, speed versus torque for cumulative. Now coming to the last type, which is differential. In case of differential, if at all we see, the differential is a motor where the net field is never stronger, right? Because the net field is the difference of the two fluxes. So the field is always going to be weaker. If that is so, the torque is proportional to phi Ia and the phi is not increasing anyhow. It is getting weaker. So what will happen? Gradually the torque would be increased, right, as it is directly proportional. But because the field is not much stronger, that's why the torque produced is also very small. So it is at the last, right? It gives us the lowest starting torque compared to all. This is differential. Right? Similarly, in case of speed versus armature current, in this case, what happened? Now we know that the speed is proportional to EB by flux. EB can be given as V minus IARA minus ISC RSC, right? Fine, but with that, if at all I see flux, this is getting weaker, which is proportional to IA, right? This is getting weaker every time. In fact, it is proportional to the current which is flowing in it, right? In the field. That means field is for both, for series as well as for shunt. And the net field, that is the difference of the two fields, not the addition. So in this case, what is going to happen? This is going to be lesser. If this is going to get decreased upon, the speed will increase. So in fact, this kind of motor gives us the reverse characteristics. What actually used to happen, when we increase the load, the armature current increases. But with the increase in the armature current, the speed will decrease. It can be seen in any kind of motor. Let that be shunt, let that be cumulative, let that be series. The speed is decreasing, right? But in case of differential, it shows us the reverse characteristics. With the increase in the armature current, this is proportional to armature current. With the increase in this, there would be, when there is an increase in the armature current, there will be an increase in the speed because the flux is getting decreased every time. It is a differential motor. It is never increasing. So the speed gets in the opposite direction. That means with the increase in the load, there is an increase in the speed, which is not the regular nature of the motor. And the same kind of graph we used to get it in case of here, differential. So these are the characteristics for the DC motor. All the 4 types of characteristics have been studied in this: series, shunt, cumulative and differential. Based upon these characteristics, we can give the applications of individual motors, right? If at all I go with the application of DC shunt, what can be the possible applications of DC shunt motor? So we have just seen what is the characteristics of DC shunt motor. A DC shunt motor is characterized by it is having almost fairly constant speed and gives us a moderate starting torque, right? So its applications are restricted to those areas where we are having moderate starting torque with fairly constant speed. So it can be fans, it can be blowers, it can be centrifugal pumps, right? It can be drilling and milling machines. Drilling and milling requires almost the constant speed, drilling and milling, right? With a slight variation in the speed. right? Lathe machines, right? So those would be giving us the applications for DC shunt. What can be the possible areas of DC series? DC series motor. For a DC series motor, if at all I see, the possible area, what is its characteristics? The characteristics for a DC series motor, if we see, it is characterized by higher starting torque, right? It is having, first point, it is having a higher starting torque. In fact, highest starting torque amongst all the DC motor what we have studied, right? And second, it is characterized by one of the property that it should never be started on a no load condition. This condition is dangerous. So I may be saying that the no load condition is dangerous, right? If that is so, its applications, if at all I say, what are the applications of these? Depending upon these. So it will be required where the higher starting torque is required. That means the areas which are basically the lifting jobs. So the lifting jobs like it can be conveyors, it can be trolleys, it can be lifts, conveyors, elevators, it can be electric locomotives, right? Or traction. So it can be conveyors, trolley, lifts, elevators, electric locomotives or traction, right? Similarly, coming to cumulative. For when we go with the cumulative, it is characterized with DC cumulative. A DC cumulative motor, it is characterized by, once again, it is having the advantage of both. What is the first advantage? That it produces a nice starting torque. It gives us a nice starting torque, a fairly good starting torque. And also the no load condition is allowed. Right? If that is so, what can be its possible areas? Now it can be having, as it is having the advantages of shunt and series both. So its application is also the combination of the both. It can be used in the fans, blowers or the conveyors or the trolleys. Lastly, coming to DC differential motor. In case of DC differential motor, we have seen it gives us the reverse characteristics. The characteristics, the very first characteristics of DC differential motor, differential compound motor, it is characterized by, it gives us the lowest starting torque. The starting torque is lowest. With that, the another one, the speed increases with the speed, the increase in the load, which is in fact, which is not the natural nature of the motor. It used to happen that with the increase in the load, the speed should decrease, right? But it gives us the reverse characteristics. That's why a DC differential compound motors founds rare applications in practicality, right? So here we are done with the DC motor and their characteristics, the torque equation, how it can be given, how the relationship is there between the torque and the flux and the armature current, the speed and the various characteristics, and how based on these characteristics we can be having the application areas. Thank you all for being with us.